So we've gotten a conceptual understanding of the human eye, but we can talk more about vision correction and actually figure out what the number of your glasses actually means. So we get these prescription numbers, and how is it related to the nearsightedness or farsightedness of our eyes? So let's figure that out. To start with, let's remember that a nearsighted person, so a nearsighted person has a longer than normal eyeball, and because of that, the light is actually focused down in front of the retina. We need to spread those rays out in order to get it focused on the retina itself. So these people need diverging lenses. And there are a lot more nearsighted people in the population than there are farsighted. I don't know why, but and there's an interesting thing. Among kids who grow up in urban environments, like tightly urban, inner city, and places where they don't have long stretches of view, they're more likely to grow up to be nearsighted. That's some interesting news I saw in Science and News one day. So a nearsighted person has a longer than normal eyeball, and so they need a diverging lens. Our diverging lenses have a negative focal length. Being diverging it defines a negative focal length. And so our prescription for lenses means we need a diverging lens and a negative prescription. If you have a negative prescription, you are nearsighted. And your lenses, if you actually look, if you have glasses, your lenses should be skinnier in the middle. So we've got skinny in the middle for nearsighted, and that's me. So a negative focal. Now, what is this prescription that we talk about? The prescription for your glasses or contacts is in a variable called power. It's a power of a lens. And the power of a lens it's the symbol capital P. Woohoo! And the unit is diopters. And you know, optics, optician, all that good stuff. So the unit is diopters. So we have power. So we have power in diopters, which is capital D. The relationship between power and focal length is really straightforward. Power is 1 over the focal length, and focal is 1 over the power. So a diopter, can you figure out what unit a diopter must be in? If a focal is in meters, if we have a focal length in meters, what is a diopter? Well, okay, if F is in meters, then we have 1 over meters. So a diopter is equal to 1 over meters, or meters to the minus 1. And so for a nearsighted person, we can figure out what their focal length is and their power, but we need to know how badly nearsighted or farsighted they are. So from that, what we do is we calculate a nearsighted person's far point. What's the farthest away they can see something clearly? So a nearsighted person like me, I can see nearsighted things clearly. Far things are blurry for me. So we calculate something called the person's far point. And that's the farthest away point that they can see something clearly. And so what we do is, okay, let's see. Without my glasses, I can see, oh boy, can I read this? I can read it about there. So what is that? Let's just say it's 60 centimeters. So let's say my far point is 60 centimeters. And I'm going to convert that to meters. That's 0.60 meters. So anything that's farther away than 60 centimeters is blurry for me. I can see things closer, but not farther. The other related idea is the idea of the near point. And we talked about this earlier when we were talking about mirrors and doing the tape on the cheek activity. So the near point, you can probably guess, your near point is the closest something can be and still be readable, still be sharp. So, dry erase, huh? Oh my gosh, oh my gosh. With this eye, it's about there. So what is that? It's about 1 foot. So we're talking 30 centimeters. So my near point is 30 centimeters, and 0.3 meters. Well, what do we do with this? Well, what the glasses need to do is they need to take faraway objects for me and make an image of that object that's close enough for me to have it be readable, for it not to be blurry. So we take an object far away, make an image at my near point. All right, so for nearsighted people, what we need to do is take an object that's far away and blurry and make an image of it that's close enough to be not blurry. So we take a faraway object, and anything more than, 10, 20 feet out is effectively infinitely far away for our eyes. So I'm gonna have an object at infinity, and what I'm gonna do is I'm going to make an image of that object at my far point. What's the farthest away I could put it to have it be crisp and clear and not blurry? So we've got far point. But let's think about images, real versus virtual images. I want, when I put my glasses on, I need to have an upright image because I don't want whoop, bloop, boop, bloop, bloop, bloop. I don't want to swap every time I put my glasses on. So do I want a real image or a virtual image? If we think about what we saw, virtual images with lenses are the only ones that can be upright. That virtual image is upright, could be smaller, could be bigger, depending, well, for converging lenses at least. And it's formed on the same side of the lens as the object. So if we have my eye here, and here's my glasses lens, and here's my object, then what we end up doing, and that's so let's say we have my eye here, and here's my glasses lens, and there's an object. We want an image of this object to be upright, and it turns out we want it to be on the same side as the object, same side of the lens as the object. So image and object, that's image, need to be on the same side of the lens. Both of these pieces of information, upright, same side, tell me it's a virtual image. And with the math for a virtual image, what did we have for DI, the sign of DI? An image distance for virtual is negative. So we need to include that. That's really a key for this. Now DO is infinity, something far away. We're going to make an image of it at the closest we can bring it and still have it and make it not blurry. So what kind of focal would I need? Well, we can just go back to our original lens equation. And DO is infinity. DI is my negative far point, which was 60 centimeters, equals 1 over F. Well, what's 1 over infinity? 1 over a very big number is 0. Isn't that nice? So the math for that just goes away. And well, if 1 over negative 0.6 is 1 over F, my focal is negative 0.60 meters. Oops, my bad. 60 centimeters, negative 60 centimeters. So what would the power be? And if you remember, power is just 1 over the focal. So the power of my lens would be 1 over negative 0.6, which is negative 1.67. And so long as this is in meters, this is in diopters. So that would be the power of the lens that is needed to correct somebody's vision who's nearsighted and with a far point at 0.6 meters, 60 centimeters. So that is the basics of the math for nearsighted people. Now let's do farsighted people. Okay, so for farsighted people, they have a shorter than normal eyeball, which means that the light that comes in, it actually gets focused down to a point behind the retina, behind our eyeball screen. And so we need to make those light rays come closer together more quickly. So we want to converge the light rays, so we use a converging lens. And a converging lens has a positive focal which means we are going to have a positive power for our prescription. So if you have a positive prescription for a lens, that means you are farsighted. And farsighted people can see far away things pretty easily, and close up things are not as easy for them to see. So what do we need to measure for farsighted people? So close up things are hard to see. So we need to take an object that's close and move it far enough back that that object is no longer blurry. It becomes clear. So we take something close, move it far away, make an image of it far away, far enough away that it's clear. So we need to know how far away we have to go in order for them to see things clearly. So what we do with farsighted people is we figure out their near point. And their near point is going to be something far away. It's not going to be the standard, and across humans we call the standard near point 25 centimeters. Yours is going to likely be different than that. So we take something and we're going to take an object close and make an image as far away as it needs to go to make it be clear. So how far away does an object need to be in order for you to see it clearly if you're farsighted? So farsighted people, we're going to take an object that is close, and we use 25 centimeters because that's what we're calling the standard near point for humans. So we're like, people should be able to see things 25 centimeters away and farther. So DO, we're going to take a close-up object and make an image of it that's far enough away to be clear. And so that's going to be somebody's near point. Virtual image again, which means we need that. So what kind of focal would we have for a farsighted person? Let's give that a try. So for farsighted, let's add that. We can do our standard equation, 1 over DO, 1 over DI equals 1 over F. Our object was close up. We take something close up at 25 centimeters, and we make an image of it at a person's near point, excuse me. I gotta be careful. And we need to figure out what this is. Now this you have to be careful. We need, if we're going to have a power of a lens, a prescription of a lens in diopters, we need everything here to be in meters. So 25 centimeters, we need to convert that to 0.25 meters. Let's say we've got somebody's near point at, let's make it pretty bad. Let's say it's a full meter out. So we have to make an image a meter out in order for it to be clear to this person. What kind of focal would they need? All right, so 1 over 1/4, well that's 4, plus -1 equals 1 over F. Okay, 4 minus 1. So 3 is 1 over the focal is positive 1/3, which is positive 0.33 meters. What would the power be? Power is 1 over the focal. Well, okay, 1 over the focal is just 3. So the power is plus 3 diopters. So positive power prescription is for somebody who's farsighted with a shorter eyeball. And we take an object close up at the standard human near point and make an image of it however far away their near point is. However, we move it out there until it's the nearest they can see clearly, and that'll give us the focal and it'll give us the prescription. So there's a little bit on how to calculate the prescription for you if you are farsighted or nearsighted. And if you are near or farsighted, I strongly recommend you take your glasses off and figure out what your near or far point is and see how close that is to your actual prescription. Give it a try and you'll see it comes up pretty darn close. It's cool. So give it a try. But there's the basics of the math for human eye vision correction. Yeah, that'll work. Good job.